Hello everyone, in this video I will explain what molecular descriptors are and I will show you how to calculate them using RDKit and Mordred. Both these packages are open source, so we can use them to calculate molecular descriptors. First, what are molecular descriptors? In simple terms, molecular descriptors are numerical representation of molecules. We just represent molecules with numbers. The question is, why do you need that? Why do you need numbers? The reason is that computers are good at numbers. So we need to have some numerical representation of molecules to do calculation using computers. Molecular descriptors are generally used to develop quantitative structure-activity relationship in drug discovery, and also we use molecular descriptors to develop quantitative structure-property relationship. Using machine learning or deep learning, we can use molecular descriptors as input features, and then we can predict their physicochemical properties like their solubilities, their activity, toxicity, yield, and so on. So molecular descriptors are very important to develop machine learning models. Molecular descriptors are generally classified into 5 classes based on dimension. The first one, zero-dimensional descriptors, are mainly deals with like molecular weight, is considered as a zero-dimensional descriptor. If you count the number of atoms in a molecule, that could be considered as a zero-dimensional descriptor, like if you calculate atomic mass, atomic charge, and so on. In one-dimensional descriptors, you will focus on structural fragments like functional groups, substituents. In this case, for instance, this is aspirin. It contains acid functional group, ester functional group, it contains an aromatic ring. Okay, so these things can be encoded, say for instance using fingerprints. The well-known fingerprint, which is a Morgan fingerprint. I'll show you how to calculate Morgan fingerprints in Jupyter Notebook, but generally fingerprints encode the presence or absence of a certain structural fragment. If that fragment is present, it will put 1. If it is absent, it puts 0. So this is just a binary encoding. So then we'll use these fingerprints as a molecular feature and then predict the activity or the biological activity or the physicochemical properties of molecules using fingerprints. There are also 2D descriptors. These are calculated using molecular graphs. Say for instance, you can calculate adjacency matrix. So in this case, it shows you which atom is bonded to which atom. So you can encode that kind of information using adjacency matrix. So if you calculate descriptors using two-dimensional structure, which means molecular graphs, these kind of descriptors are called 2D descriptors. There are also 3D descriptors. In this case, you need to have the atomic coordinates. You need to have this information to calculate 3D descriptors. Most of the time, the quantum mechanical descriptors are 3D descriptors, because when you calculate these quantum mechanical descriptors, you need to have the 3-dimensional structure of the molecule. They usually do energy minimization and geometry optimization. If you calculate descriptors using the 3D structure of the molecules, they are called 3D descriptors. The last one are called 4D descriptors. These 4D descriptors model the interaction between molecules. If you calculate descriptors based on the interaction of molecules, say for instance in the case of protein ligand interaction, these kind of descriptors are called 4D descriptors. Okay, now let's see how to calculate molecular descriptors using RDKit and Mordred. The first thing we need to do is we need to import these modules from RDKit, all chem, descriptors, molecule descriptors from RDKit. We need to import pandas to read CSV files, Numpy, and from Mordred we need to import calculator and descriptors. Let's run the cell. So now we are imported all these packages. If you want to run this notebook using your computer, you need to install Mordred, Numpy, pandas, and RDKit in your Anaconda environment. But you don't need to do that. I'll give you a link so that you can run this notebook in Colab. But if you wish to do it in your computer, you need to install these 4 packages. Okay, now let's read the CSV file. This CSV file, I obtained it from a publication. You can have this link. You can use this link to see it. So what it contains is, it contains smile strings and the corresponding HUMO-LUMO energy gap values. There are 2,904 rows and 2 columns. Okay, so the first column contains smile strings, and the second column contains the energy gap, that HUMO-LUMO energy gap obtained from, I believe, from density functional theory calculation. Okay, so what's important for this purpose is the smile strings. The first thing we need to do is, if you are working with smile strings, you need to generate canonical smiles. The reason is that you might have more than one valid smiles representing a single compound. So ideally we need to have one smile representing one molecule, but practically you'll have more than one valid smiles representing a molecule. So you need to generate canonical smiles. You can use RDKit. Just basically there are 2 lines of code to achieve that. In the first case, it will read smile strings and it will convert to molecular graphs, and then you will give that molecular graph as an input, and it will convert it into a smiles. Okay, so this is a very simple function. So let's see what I mean. So in this case, if you look at this smile, you have a double bond in the first carbon here, right? So let's see how it looks like. Let's look at the structure. So you have a double bond at the first carbon here. If you put the double bond on over here, you'll have this structure. For a chemist, these 2 structures representing one molecule, but the computer thinks these 2 structures are different. Okay, let's see what the computer says. Is A equal to B? It says false, which means the computer thinks that these 2 molecules are different. But for a chemist, these 2 structures are the same. That's why we need to generate canonical smiles. Let's give this smile for the functions that we defined over here. Let's see. Canonical smiles. So I didn't run it, maybe, so I have to run this one. Okay, so let's pass this smile to the function and see its representation. Yeah, it gives us as it is. What happens if you give the second molecule, which was B? If you remember this, the double bond is over here. If you give that, what does the function give us? It gives us the same representation. So that means this molecule and this molecule are the same. We can check that using C equal to D. In this case, it is true, so they are duplicates. So we need to have this kind of representation. We need to generate canonical smiles so that we can easily remove duplicates. Okay, now let's pass the smiles to the function and generate canonical smiles. So once we generate the canonical smiles, we need to replace smiles column. Okay, so then we'll put we need to replace this smiles column with the canonical smiles. That's what we did over here. Okay, so there's no change over here, still the number is the same, but in this case we can identify duplicates. Okay, so let's see if there are duplicates by running this cell. Yeah, so it says that there are 31 smiles, duplicate smiles. Okay, now let's filter these duplicate smiles from the data set. So if you filter them and sort them by smiles, you can easily identify duplicates. So yes, these two are duplicates, even the energy is the same. Okay, these two are duplicates, so the list goes on. So these are the duplicate smiles. So we don't need to have duplicate smiles, we need to remove duplicates, we need just one representation. So what this drop duplicates does is it removes duplicate smiles. So only keep one smile and remove the duplicates. Okay, so the number now decreases from 2904. If you remember, these are the number of rows, 2904. When the duplicates are removed, okay, now the number becomes 2873 rows. Now we remove the duplicates. We have this data. This is a cleaned data. We don't have duplicate smiles here. We need to use this clean data to calculate molecular descriptors using RDKit. So it might be difficult for you to understand each line of code, but the easiest thing to do is we need to run each line of code separately and try to understand how this function works. So in the first case, what it does is it takes smile strings, and convert that smile string into molecular graph. This is a list comprehension. Okay, that's the beauty of Python. So when you give many smiles, it will convert all these smiles to their corresponding molecular graphs. That's what it does in the first line. In the second line here, it calculates all the descriptors that are available in RDKit. Let's see how it works. Let me copy this this cell and paste it over here. Okay, and then cal. Okay, yeah, but in this case it shows me an object. To get the descriptor names, I need to use this function, get descriptor names. Okay, this one basically gives us the descriptor names. Okay, control V. Okay, so these are all the RDKit descriptors. There are about 200 descriptors, so you can calculate all these descriptors using this function. So these are the descriptor names. So we need to define an empty list for these molecular descriptors, and then using this for loop, for each molecule we need to add hydrogen to it. We need to add hydrogen to each molecule, and then we need to calculate all these 200 molecular descriptors using this function. Once we get these descriptors, we need to append them into the empty list over here. We'll do this for each molecule, and finally this function will return the molecular descriptor values and the corresponding molecular descriptor names. And then this is how you call the function. You just pass smiles. Okay, and then once we get the molecular descriptors and descriptor names, we can put them in a table. right? Let me run this function, and then you need to put it in a table using pandas data frame. So it generates a spreadsheet so that you can easily see descriptor names and the corresponding values for each molecule. It may take some time. Okay, so we have these 200 descriptors, and it calculated the molecular descriptor for each molecule. How many molecules do we have? We have 2873. Sorry, for each molecule it will calculate 200 descriptors. So we'll have this table. Okay, so this is how you calculate molecular descriptors using RDKit. In RDKit you can also calculate molecular fingerprints. One of the most commonly used molecular fingerprint is Mordred fingerprint. So in this case I'll show you how to calculate Mordred fingerprints using RDKit. So here I defined a function. So this function basically accepts smile strings. Here is an empty list. For each smile for each smile, it will convert that smile into molecular graph, and it uses that molecular graph to calculate Mordred fingerprint. So you need to pass the radius. This is the radius of the Mordred fingerprint, and this is the length of the fingerprint. So in this case 2048, which means you'll have 2048 columns. Once you get the Mordred fingerprint, we need to convert into Numpy array. Okay, that's the reason we have here, and then we need to append that Numpy array into the empty list over here. It will keep doing this for all the data we have, and then finally it will return the list as a Numpy array. Okay, let me run this one. So it's a Numpy array. You can see the number of rows and the columns. Okay, so this is the number of data points we have, number of smiles we have. Here are the fingerprints for each data point, for each smile. Okay, we can put that in a table using pandas data frame. Okay, the column names, you can generate column names using this. All right, so we have fingerprints for each molecule. The length of the fingerprint is 248. There are 248 columns. Okay, you can also change this size into, say, 1024, say, for instance. The reason is you might have a very sparse data, so many zeros. So to reduce that, you can change that length into 1024. Let me run it again. Okay, in this case, you know, we can change the bit length into 1024. Okay, so you'll have 1024 columns. Okay, so this is how you calculate molecular fingerprints using RDKit. Now let's see how to calculate molecular descriptors using Mordred. There are 1826 descriptors in Mordred if you include 3D descriptors. You can achieve that using kind of 2 lines of code, 3 lines of code, right? I defined a function over here. So the function accepts smiles, and then it will calculate descriptors, right? For each smile, it will convert into that smile into moles. Okay, molecular graphs. For each smile, it will convert into molecular graphs. It will use that molecular graph to calculate all the 1826 molecular descriptors, and then finally it will give us back the data frame. Okay, let's see how it looks like. It may take some time. Let's see the shape and let's see the table. Okay, yeah, so it calculated 1826 molecular descriptors for each molecule. So we have this table, right? These are the descriptor names. Okay, so as I said before, you can run this notebook in Colab. There is a link in the description, so you can follow that link. So you can click on this link to run it on Colab. Just click this one, right? So you are in Colab now. So the first thing you need to do is you need to copy it in to your drive. So just click on this one. Okay, so you have the copy of the notebook here, so you can change the name if you want. The next thing you need to do is you need to go to runtime, and then you can change the runtime type. I would prefer to use the GPU. Just change to GPU and save. You need to install these two packages, RDKit and Mordred. So in this case you are installing RDKit and Mordred. So you can run cell by cell, or you can run all of them at one time. So that is already installed. So these two packages are installed. Next thing is you need to import them using this cell. You need to import RDKit and Mordred. Okay, they are imported. Let's read the data. Okay, so we have 2904 rows and 2 columns, the same as what we had before. Okay, so these are the smiles. So you can generate canonical smiles. So you can run cell by cell just like this, or you can run all at once. So if you say run all, it will run all the cells. Okay, it is calculating RDKit molecular descriptors, and this function is mainly used for that purpose. Okay, yeah, it's done. And also calculate fingerprints. This is also done. Yeah, so the next thing is calculating descriptors using Mordred. In this case it takes kind of about 8 or 9 minutes. I don't know why it is slow, but it takes a longer time. It didn't take that much long in my computer, but in Colab for some reason it takes a longer time. Okay, now it is done. It calculated all the available molecular descriptors in Mordred. There are 1826 molecular descriptors. I hope this video would help you to calculate molecular descriptors and use them for your projects. If you like this kind of videos, please subscribe this channel.